So this is where I talk about the metric system. Now, if we lived in any other country, and some of you have traveled to other countries, so you know this, everything's a metric system, and it's much easier. It's all just based on the number 10, and you move decimals around and you get the right numbers. It's much, much easier, but we don't use it. And I talked about this in integrated one. Usually I talk about it every time I do a dimensional analysis. So a few of you might actually remember hearing this. Back in the 1970s, we tried to actually put a bill through Congress to have the country change its system from the standard system to the metric system, because everyone else in the world was going to it. Right now, there's only 3 countries in the world that don't use the metric system: the United States, Liberia, which is in Africa, which is the country that in the middle 1800s they tried to send former slaves there to colonize it. So it would be a way of moving slaves out. It was a mostly failed attempt, except they actually did get a few people and start a country. Capital of Liberia is called Monrovia, after one of our presidents, in fact. And it's now a country in Africa. It's not thriving that well. It's poor country. But they follow a lot of things the U.S. does, including using the standard system, not the metric system. And the third one's Myanmar, and I have no idea why Myanmar uses the standard system and not our system. Not the metric system. I have no idea. But that's it. Everybody else in the world uses the metric system. But in the 1970s, when we tried to start that, the auto companies in Michigan decided that it would be too expensive for them to change all of their factories and all of their tools and change them all to the metric system. So they lobbied Congress and probably spent a lot of money trying to convince congressmen and senators to vote against the bill. And the bill failed. And nobody's ever tried to get it changed since then, but the bill failed, and so we're stuck with the standard system because nobody wants to change the metric system completely. Some things do, some things come in metric. And if everybody decided they wanted to change to it, we would do that. But most people just don't care enough to do it. The auto companies then started having a problem the next 10 years after that, because a lot of companies in Asia and Japan in particular started sending cars over here, and Germany did the same thing. People started buying those cars and liked them. So the car companies were losing money. They decided to start selling cars in other countries around the world. And they started realizing that everybody else uses the metric system. So they had to change their factories to use the metric system for those cars to sell other places. But they had to keep the standard system for the cars in the US. So now the factories over in Michigan making cars have to use both standard and metric system. And so they basically have wasted a lot of money trying to keep everything both instead of just moving everything to metric system. That's called short-sighted. So in order to save money temporarily in the 1970s and 80s, they have spent a lot more money afterwards trying to do both systems at one time. So one of my little pet peeves about it, because teaching math would be a lot easier if we didn't use standard system. Ever since you were first grade and up, it would be so much easier if everything was metric system, because it's just intuitive. It's much easier to use. But we're stuck, so we have to do it. In this kind of case, though, we're going to go back and forth between metric system and standard system. Because we're going to do that. And you do that already. You see that in science. Much of science tries to use the metric system for most things. That's sort of an attempt to change to it, because around the rest of the world, all the scientists use it. All the papers and conferences and everything is in the metric system. But we're stuck here. So how many cups are in 15 liters? So you're going to change from cups to liters. And I've given you conversion rates. On the test, I'll be giving you conversion rates. I won't be making you figure out what they are. You don't have to memorize them. But I'll give you some. But in this case, notice these conversion rates are not cups directly to liters. I have it set so you have to change from cups to quarts and then quarts to liters. Or the other way, you have liters, so we're changing from liters to quarts and then from quarts to cups. So that looks like what we're going to do, because we have liters, we want it in cups, so we're going that way. So what we do is 15 liters. So if we want to know what that is in cups, it looks like we'll use this conversion rate. So one of these liters would be 1.057 quarts, which tells you a liter is 4 quarts in a gallon. So it's about a quarter of a gallon or something. So if you think about milk that you buy, you really buy in a thinking gallon now. So a quarter of that would be a liter, approximately. I want that dot out of there. So one of these liters would be 1.057. So in order to get it to quarts, all we have to do is multiply by 1.057. And when we do that, somewhere I think I got that written out, but I think I can't find it. I'll use my calculator with it. Oh, no, I do have it here for this one. Okay, so if I multiply by 1.057, I get 15.855 quarts. But quarts is not what I want. Cups is. This one tells you that each quart is 4 cups. So if I have 15 plus of them, all I have to do is multiply by 4, and I'll have how many cups? So that's equal to, for cups, this is also an approximation now. And so I'm approximating these, because even these are approximations. So the approximate number of cups is 63.42. We do not talk 63.42 cups. You would probably say about 63, 63 and a half, at most 63.4 cups. So I want you to be precise, but precise in this kind of case means like 1 decimal place. Or if you round it appropriately to the same, to the ones place, then that would be good. But 0.4 is almost halfway. If it was 63.2, I'd say round it down to 63. But this one's a little too much in the middle. So use conversion rates by thinking about what makes sense. What do I multiply to get to the next one? That's if you're doing a single unit change. So here we're doing another single unit change. So we have to go from 12 feet to centimeters. So I'm going to go from 12 feet to inches first, because there is no feet to centimeters here. And then I'm going to go from inches to the centimeters. Well, feet, there's 12 inches in a foot, so it's just 12 times 12. Okay, that's that one. And now I have a couple of choices. I can do that 1 inch is 2.54 centimeters, or 1 centimeter is 0.394 inches. So you have to think about which one of these would make sense here in this. Well, in this case, one of these times 2.54 would give me what I want. So 144 of them times it would give me what I want. So what I need to do is this one. So I'm going to multiply times 2.54. When you multiply by that, you get 365.76. Now in this one, it makes no sense to even go 1 decimal place, because you got 360 something of these. You got so many centimeters that part of another centimeter, you just roll that in. And so the best answer for this is approximately 366 centimeters. Whoops. Oh, okay, good enough. Okay, now come slightly more complicated problems, because now we have to change 2 units. And there's a couple of ways to do it. You can actually do what I did up there and do it like a couple of times and do it with both the top thing miles and the other one hours. But I'm going to show you a different method with proportions. I like this one because it helps you know where to cancel out the units. And this is one of those things where there's a couple of ways to do it. This is just one way, but it's one that appeals to me, so I get to show it. So 5 miles per 1 hour. So a fire spreads at that speed. What we're going to do, 5 miles per hour, it doesn't give you a sense of how fast that is. Is that a slow move or a fast move? Is it something that, I mean, fires are always dangerous, but is this so dangerous that, you know, it would catch up to you really fast if you were running away from it? Well, let's figure that out, because in meters per second, if it's like a quarter of a meter per second, well, that's not very far. It goes fast, but you can probably get away from that if you're paying attention. But if it's a couple of meters per second, then that's really fast. You can't run that fast. I'll run it. So let's just get an idea of that. But the point here is to change from miles to meters and from hours to seconds. So what we're going to do is make a proportion with miles on the bottom so that I can cancel out those miles. So when I look at the conversion rates, I'm going to change from miles to feet, and then I'm going to change later from feet to meters. So first we will use this one because there is no miles to meters on here. Since there isn't a miles to meters, we're going to have to do it in 2 steps because that's all that I gave you on purpose. So I'll do that too on the test. I'll give you one possibly where on purpose you have to do 2 steps, just like this. Or I might not. If it's 1 step and an easier, good deal. The next one is like that. So there are 5,280 feet in 1 mile. But in doing that, the miles are gone now. But I don't want feet either. So I'm now going to multiply to have feet on the bottom. That means I'll now use this one, meters, 0.3048 over 1 foot. So 1 foot is about that many meters. But by doing that, feet are gone. And I have the meters that I want for the end. Now I have to do it with the hours. I have to put hours up there so I can cancel that out. I'm going to do hours to minutes, 1 hour, 60 minutes. And there goes the hours. But I don't want minutes either. So I want to get rid of those and make them seconds. So 1 minute is 60 seconds. Now I've gotten rid of the minutes. If you remember that there are 3,600 seconds in an hour, and you can just do that directly and you don't have to do it minutes. A good half the time that I do it, I lose a 0. So I have learned not to trust myself. That's why you'll always see me doing a 60 and 60. Even though I could do it in 1 step, I'll do it in 2 because I'm more certain of not making a mistake. That's one of those things when you get used to doing something, you realize there's something you have to watch out for because it's a common error you can't seem to shape. You find a way around it. My way around it is to do the 260. Having said that, I've talked about this for so many years that I probably will never forget again. It's 3,600. But I've never forgotten doing that in class a few times in front of people. It was embarrassing. So now I make sure I always do 60 and 60. So I am left here with a 5 times a 5280 times 0.3048. And on the bottom, a 60 times a 60. So I'm going to multiply across and then divide by the 3,600. And when I do that, I get, I don't have the answer right now here, so I'll use my calculator and do it. 5 times 5280 times 0.3048. So actually comes to 8046.72. I'm going to divide that by the 60 times the 60. So I'll divide by 60 and divide by 60. And that's approximately 2.2352. And it's meters and seconds. Now, this needs some rounding. And so when I look at it, the 5 would make it a 4, but more likely that 3, we just don't need most of that. So the best answer would be 2.2 meters a second. Now, a meter, there's a little less than 50%. That means in 1 second, a fire would go almost in 2 tables like that. So that means 2, 1, 2, 3, 4. In about 5 seconds, it will go right through this entire room. I can't get out of this room in 5 seconds. That's fast. That's too fast. Fires are dangerous, but fast fires are bad enough that firefighters fighting them, if the wind turns and starts coming back at them, it's very dangerous for them. And that's why we regularly, every year in this state, we tend to lose 2 or 3 firefighters to fires that are just really dangerous. And they turn back, the wind gets them, or something happens and the fire goes faster than they expect, and they, and then it's not a safe thing to do. And this is mathematically sort of why, or sort of mathematically shows you how fast that one of them can go. I forget where I first learned, got the example of 5 miles an hour, but it's a good one to illustrate how fast a fire can go in our dry seasons when there's not much rain or anything. One more problem to look at. And this is the same exact kind of concept, but now we'll actually have one less step because we're going from gallons to liters, and there's a gallons to liters conversion. So I won't have to do this as a 2-step one for the top. I'm going to do the same kind of 4,000 gallons over 3.25 hours. And this is a lesson for you to make sure you put things in decimals. It's just much easier than dealing with them for fractions most of the time. Your choice, really, but it's much easier. If I do it like this now, I want gallons to get out of there. And I'll use this. 1 gallon is 3.785 liters. And that gets rid of my gallons. And now I'll do the hours. Hours on top and minutes here. So 1 to 60. And 1 minute to 60 seconds. And so now the hours are gone and the minutes are gone. And so I'm going to multiply that across and divide it by 60 and 60. And when you do that, you come to 1.3. It's actually 1.294 liters a second, but you definitely want to round that. So it makes more sense to say 1.3 liters a second.